Hello. I was honoured to be asked to give the keynote address for the 2014 UK Annual Systems Engineering Conference. 2014 was the 20th anniversary of the UK chapter of INCOSE. 20 years previously, I had held the BA Systems Chair in System Science at RMCS Rivenham, and it was from there, with BAE's help and support, that we inaugurated the UK chapter, and I was its inaugural president. And yet only 1 year later I had to retire on medical grounds. So unfortunately I was only able to watch the fledgling chapter grow and develop from a distance. In returning then for this one-off performance, I was asked if I would review how systems engineering had progressed in those 20 years. Hence, respice, adspice, proscipe. My old school motto: look back, look around, look forward. So, respice. How far have we come? Since the 1940s, when systems engineering started in earnest. Here's a sort of time map showing the various lines of progress. On the left-hand side you can see time from 1940 all the way up until 2020. And the next column, operational systems engineering, refers to UK air defence, with the Battle of Britain, which as we all know took place in 1940-41, and then UK air defence, linesman mediator, IUCAD, which is improved UK air defence ground environment, UK air command and control information system, the air command and control system, and the air defence command information system. And you can see in the next column, high performance aircraft systems engineering. We have a number of interceptors, starting off with the Vampire and Meteor, then the Hunter and Javelin, the Lightning Mark F1, and then the F Mark III, the Phantom, Tornado air defence variant, Tornado F Mark II, and currently we have the Typhoon. Missing out the INCOSE list, we go over to the right and we see that the US was also developing, starting off with atomic and nuclear power generation, then Polaris, Project Gemini, NASA Apollo, Aegis, which is the US Navy's Fleet Air Defence, Integrated Air Defence System, and Trident, and the Strategic Defence Initiative. You can also see that there were various things going on in the way of defence acquisition programs, top right and top left, with the US and the UK respectively. Referring to the INCOSE column, it didn't really get started until about 1990, where the dotted line came, which was the end of the Cold War. And almost immediately it seemed to divide. Although it's announced to be the INCOSE International Council on Systems Engineering, it seems to be more concerned with the engineering of systems and defence engineering management. However, there we go. The UK's record on developing aircraft was significant. The near one is the training version of the Lightning, the T4, and the far one was the mythical TSR-2, which never really got far from prototypes. Fine aircraft, the pair of them. Back coming up to 1978, this is what systems engineering management looked like in the UK. And you can see it reads from the bottom to the top. You can see it starts with understanding and specifying the requirement, and then going up through various design factors, and the center panel there, the center line going up, goes through implementation, integration and test and trials and so forth, all the way up to update and evolution. On either side we can see the supporting management things, so we've got systems engineering, management and planning on the left, and maintaining an audit trail, which turned out to be very important. Modelling and simulation to predict effectiveness on the right, and so on. And that was quite a sophisticated management plan for the era. There was a co-evolution of systems engineering. In the 70s, the US defence and aerospace people developed systems engineering tools and methods, which were brought to the UK and the rest of Europe by the Technical Marketing Society of America. They introduced this to Robert Larno's matched toolsets, for example, with n-squared charts from TRW, data state design from IBM, RNets, that's requirement nets from Hughes, and structured analysis, which was about functions and hierarchy and to do with software. At this time, the US and the UK systems engineering were both on the same page, both systems theoretic and both effectively applied system science. Moving on a little bit further, we come to 1988. This is an example of my own work. When I was at City University, we developed a system design for a channel crisis management system, a command and control system. Curiously enough, there's a current one being set up between the French and the English police in Calais to deal with the problem which we anticipated back then, but which was not gone ahead with because it couldn't be afforded. No, it can't be done without. Interesting. And then, with the end of the Cold War, US systems engineering fell apart as missile contracts ended and the defence and aerospace companies reorganised. Similarly, UK systems engineering fell apart as UK systems houses defence contracts dried up. So both countries lost their different systems engineering centres of excellence just at the same time when INCOSE was born, ostensibly to combat the shortage of systems engineers in the US defence and aerospace. Only there was a problem. Systems engineering methodologies, particularly in the major US companies like TRW and Hughes, had been commercially sensitive. So no one knew or remembered what systems engineering was or how to go about it. At least not the people who came into INCOSE. So there was an importance to be considered in defining. A reasonable definition of a system was vital at the outset for the nascent INCOSE. It should put everybody on the same page and lead to an understanding of what systems, the systems approach, systems thinking, system science and systems engineering were to be about. So the early INCOSE definition for system was system, an interacting combination of elements viewed with regard to function, which was really quite obscure and didn't give any clues as to the systems approach, systems thinking, system science, or even systems engineering. Then there was the early INCOSE definitions for systems engineering. Systems engineering is engineering done properly, which is engineering. Or systems engineering is multidisciplinary engineering, which is also engineering. Systems engineering is an engineering discipline, an interdisciplinary process with customer and stakeholders' needs, high quality, trustworthy, cost efficient and so on, which is actually describing not systems engineering at all, but engineering management. So ignoring all prior experience, system science, theory and practice of systems, and the outstanding heritage of world-class US systems engineering, INCOSE, followed by INCOSE, set out on an engineering and cybernetics path. Although cybernetics was not explicitly nominated, it was evident in the choice of definitions. Nothing wrong with either engineering or cybernetics, but how could it be systems engineering without systems? And by the way, the solar system was no longer to be considered a system according to INCOSE in 1992. And speak here, where are we now? What is the state of contemporary systems engineering? And are today's systems engineers capable of creating a modern version of Aegis or Linesman, or perhaps even better? Where are we now? We're confused. Well, most of us are. Look at the list of papers for many systems engineering conferences and you'll find that half to two-thirds of the papers are not systems engineering but technology research, publicity for some ongoing project, engineering, project management, or engineering management. INCOSE is confused. There are factions trying to reintroduce systems and system science, but it's like trying to change the direction of a supertanker heading full steam for the rocks. Is systems engineering an engineering discipline or something else? And if so, what else? What is systems engineering management? Is systems engineering about systems or about technology? Is systems engineering the same as engineering of systems? If not, what's the difference? What is soft systems engineering? Is systems engineering applicable to enterprises, organisations and industry? And just what is systems thinking and the systems approach? Is there a theory and science of systems and systems engineering? If so, how should we use it? What are systems and systems engineering principles? How do we apply them? So are we in danger of overlooking the fundamentals that made systems engineering unique? I'm afraid we are. So just what is a system? Well, the idea of system is of an organised whole, something complete. And you'll notice from the definition I've given at the bottom, complex whole, organised body of material or immaterial things, set of connected things or parts. That this dictionary definition comes from 1946. So this is nothing new. The idea of what a system was had been around for ages and was deliberately ignored by INCOSE for reasons which I find quite inexplicable. Anyway, the idea of systems is of an organised whole, something complete. And nature makes organised wholes, never without organisation, never incomplete. So there's the solar system, star clusters, biospheres, cultures, weather, human cells. And man-made systems are essentially the same idea. They're people-organised wholes or man-made wholes. Whole aircraft, whole robots, whole organisations. Whence holism and holistic. So we need to get that in our minds. It's a complex whole, an organised body of material or immaterial things, and a set of connected things or parts. Later I'll show you a more complete definition, but that should hold us for the moment. Self-organising system. Galaxies, a self-organised system. Dust clouds, clouds of stars, star clusters. Ecosystems, groups of interacting communities, and environmental factors. The sun's a self-organising system. It has 3 concentric shells transferring energy from the core to the sun surface and beyond. And you and me. That can't be me because I have beautiful grey hair. However, we can see there a self-organising system with its lungs, its heart, its liver, its kidneys, and its internal tubes and things, plus its veins and arteries, red on the port side and blue on the starboard side. And that's a very sophisticated self-organising system. Looking a little more closely, we can see that it's actually made up of 11 or 12 so-called organ systems, the number depending on how you go about dividing them up. The circulatory, endocrine, immune, skeletal, integumentary, which is skin, hair and nails, the outside shell as it were, respiratory, reproductive, nervous, muscular and digestive. All of these have to be in place and they all have to be interactive and they all turn out to be mutually interdependent. This body that you and I are sitting in is a truly sophisticated, well-organised system. To try and understand systems, I introduced something called, by my students, the Hitchins poached egg. And you can see a system of interest in the 4 o'clock position, and that contains subsystems with interactions between them, interconnections. And the system of interest is connected within the operating environment of the containing system to 3 other sibling systems, and there are interconnections. This actually can be used to look at and explain and categorize any system you like to mention. because it presents a simultaneous network and hierarchical view of systems. The hierarchical view you can get by looking in. If you look into the containing system, you see these sibling systems. If you look into the system of interest, you see subsystems. And were you able to look into each of the subsystems, you would see subsystems, and so on. A useful, very simple idea, completely inconsistent with INCOSE's definition of system, of course. Networks of open system, entropic cycling. This is the lifetime pattern for all systems: civilizations, ecosystems, multi-node networks, financial systems, transport systems, social systems, health systems, large-scale IT systems, complex systems, conflicts and wars. Entropic cycling is universal for self-organizing and for man-made systems. We tend not to look at our man-made systems this way and our social systems, but they are in a state of continual flux. And sometimes they collapse only to recover, and sometimes they stay apparently stable with what we call homeostasis, which is dynamic stability. And none of this need be anything to do, by the way, with cybernetics. There's no necessary feedback involved. So all the systems that we have are forever going wrong, becoming slightly unstable, and then correcting themselves, and it's a continual variation in entropy, entropic cycling. Levels of organizational integration are considered here, and you will see as this diagram builds what the parallels are. The smallest item of life is a cell. Many cells interact with each other to create a tissue. The emergent properties of many tissues go to form organs. The emergent properties of many interacting organs go to create organ systems, and so on up the chain. Many organ systems interacting create the organism, and so on. You can do exactly the same for man-made systems, where the equivalent of the cell is the active component. Tissues become composites, organs correspond with subsystems, the organ system corresponds with system, and the organism corresponds, loosely I suppose, with a platform. Populations correspond with groups, communities with companies, ecosystems with organizations, and biospheres with nations. And we can also see that there are systems engineering varieties. At the bottom we have not systems engineering so much as artifact engineering, bringing composites and components together. And then we have product subsystems engineering, making subsystems. Project systems engineering, doing systems and perhaps platforms. Then business systems engineering, industry systems engineering, and finally at the top, socio-economic and societal systems engineering. So let's define a system. A system is an open set of complementary interacting parts with properties, capabilities and behaviours emerging both from the parts and from their mutual interactions to create an integrated, unified whole, existing in and interacting with an environment comprising other interacting systems. To expand the definition, systems are wholes, complete. Systems have internal organisation with a full complement of interacting subsystem parts also having the characteristics of systems. Systems exhibit properties, capabilities and behaviour, emergence, that are not exclusively attributable to any of the subsystem parts and which may not even be of interest at subsystem level. Systems have an internal environment. Systems exist within an environment. Systems and their subsystems are open. They exchange energy, information and substance with other systems, and they adapt to the exchange. Whence we might describe systems engineering as making wholes by integrating the complete set of subsystems. It really ought to be that simple, but first, of course, establish your subsystems. Notice there's no mention of technology or people or enterprise. It's irrelevant. So what is the much touted essence of systems engineering? Choosing the right parts, bringing them together to interact in the right way, and in orchestrating those interactions to create requisite properties and behaviour of the whole. such that it performs with optimum effectiveness in its operational environment, so solving the problem that prompted its creation. So it's a loop exercise. Note how systems engineering flows directly from the definition of system. So POACHED, where are we going? INCOSE UK, that is. Well, we have to recognise that systems engineering is a distinct enabling discipline with its own principles, theory and practice. Systems engineering is the art and science of creating systems. Well, we should establish a generic INCOSE UK system science-based systems methodology. Folks really do need to know how to go about systems engineering, and it's not rocket science. We need to foster improved systems methods and tools to understand and evolve the relationship between engineering project management and systems engineering management. They're not the same thing, but each needs the other. We have to get to grips with human behaviour, and we have to get to grips with chaos and self-organised criticality and entropic cycling in systems of all kinds, because these are the norms, even though we, as engineers, try to avoid the facts. Systems engineering principles. There are basically four: holism, organicism, synthesis, and emergentism, which really puts the others together. High-level properties emerge out of lower-level properties to which they cannot be reduced. All the above are incompatible with systems engineering and the practice of reduction. So systems engineering definitely does not equal engineering of systems. The systems domain. We can see the systems domain at the top and the real-world domain at the bottom. So we start with a real-world problem at the left, and we end up with a real-world viable solution at the right. And we employ the systems methodology in the top panel. Engineering is involved if we have to make and develop particular items. And you can see how this works. We start off with a symptomatic problem, bottom left, in the real world. We transform it into a system model of the situation which exhibits the same symptoms. We postulate system solutions and concepts of operations, CONOPS. We design the whole from interacting subsystems. We create systems integration and test facilities. We integrate, test and prove the solution in context. Meanwhile, while we're designing the whole from interacting subsystems, we have specified a matched set of specifications for the whole in its context, for the parts, for their interactions and interconnections, for the organisation, management, staffing and training and so forth. And also in the real world there is a process of making, developing, buying, recruiting, training and organising. The parts of the system to be integrated are brought in and under integrating, and then integrated, tested, proved, and the solution in context is then provided and delivered with a transition to use and support as the as the real world viable solution. I beg your pardon. It's not that complicated. It really is fairly straightforward, but it does have to be understood. So both US and UK systems-based systems engineering is struggling to flourish at INCOSE at large. Meanwhile, systems are becoming inexorably more complicated. Systems of all kinds: global systems, systems of systems, media systems, medical systems, health systems, and they're all susceptible to self-organised criticality. INCOSE systems engineering is falling well behind, continually mistaking systems engineering for engineering and engineering of management, to the detriment of industry and society, which has engineering and engineering management in plenty already. Systems engineering faces the challenge of creating, operating adapting and enhancing today's and tomorrow's complex and large-scale systems and networks of systems. And that's more challenging even than the systems engineering of the 50s to the 80s. So, INCOSE UK has the science, experience and drive to reinvigorate systems engineering and to restore and enhance our ability to solve complex problems and to address complex nonlinear systems of today and tomorrow. How? Well, one immediate requirement is to develop and deploy corresponding UK INCOSE systems engineering methodology. It all boils down to doing that. Can we continue to step up to the plate and avoid being seduced by the dark side? Of course we can. Thank you for listening.